Hello again. In this video we're going to be talking about how seasonal forecasts are generated. And to help me do that we have two Phils. First up, Dr. Phillip Davis from the monthly to decadal team. He's here to tell us about the main method for producing seasonal forecasts and how we deal with the uncertainty that exists in the forecasting process. Welcome along, Phil. First things first, just let's go back to basics. How do we generate a seasonal forecast?
So a seasonal forecast usually relies on something called dynamical methods. Dynamical modeling just means it's just a way of describing the physical processes that describe the climate system and therefore drive climate variability. The climate model is very much similar to what's used for weather forecasts and climate predictions, and we have some sort of way to describe the physics that drive the atmosphere, ocean, land and sea ice. So to do this, the models use a three-dimensional grid which covers the entire globe, starting at the bottom of the oceans all the way to the top of the atmosphere. This can be imagined as many thousands of cubes or grid boxes on and above the Earth's surface and beneath the oceans. The model solves mathematical equations that describe basic physical processes to predict how the atmosphere and ocean in each grid cell evolves with time, as well as describing how the grid box interacts with its neighbouring cells. So these equations require millions of calculations using supercomputers. Before the model can be run, however, it must be set up so that winds, temperature, humidity in all of these cubes resemble as closely as possible those observed in the real climate system at the forecast start time. And these are known as the starting conditions or initial conditions. So the initial conditions for these grid boxes are obtained from observations, and these observations are taken from ocean buoys, weather stations and satellites.
And talk us through what are the advantages and maybe the disadvantages of this system.
So the advantage of these dynamical models is that they're very realistic. They're very sophisticated and they try to model the physical interaction between the different components on the planet. So they try and model the interaction between the atmosphere, the ocean, the sea ice, as well as the land. So they try and model reality as best as possible. The disadvantage is, as you can imagine, with having to deal with all these mathematical equations in all of these cells, is that it's very computationally intensive because we need a supercomputer to do this and there's a lot of manpower behind this. On top of that, you're generating a lot of data, so it's also very data intensive. In addition, even though we've been developing these models for many decades, they're still not perfect, and of course, errors are to be expected.
So it requires a supercomputer,
Absolutely.
It generates a lot of data, and it requires a lot of manpower as well. So I guess not everyone can be making these seasonal forecasts. Just talk us through who makes seasonal forecasts using these dynamical models.
So at the time of recording this video, there are 13 centres across the world designated by the World Meteorological Organization, or WMO, as global producing centres of seasonal forecasts. A list of these forecast models and their characteristics are listed on the WMO Lead Centre website. The characteristics of these models from the 13 centres varies, and therefore so does the forecast output. For example, some models only simulate this atmosphere, whilst other more advanced models also simulate the ocean, sea ice and land surface, with the most advanced models being known as coupled Earth system models. Earlier we spoke about the grid boxes that models use to cover the Earth, and it's the size of these boxes that determines the model resolution, and this also varies between models. For example, here is the model's representation of ocean currents and different resolutions. So the output on the right uses larger 80-kilometre grid boxes, which is a relatively low resolution, and the output on the left uses smaller 5-kilometre grid boxes and so has a higher resolution. You can see that much more detail is captured in a high-resolution case, just like a high-resolution television or photograph. However, the downside of these high resolutions is that they require more computational power and they don't necessarily provide a more accurate forecast.
So lots of different models, lots of different resolutions. How do you know which one to use?
So that's a good question, and we talk about different ways to assess a model's performance in the next video. It's important, though, not to rely on individual model, but instead to look at the output from various models. There are online data portals which allow you to compare and combine multiple models, and we talk about these in the final video. Most centres run their models to cover the next 6 to 7 months, and this is repeated each month. Therefore, the seasonal forecast for the June, July and August season would first be available in March, and it would be updated in April and then again in May.
Now, Phil, we mentioned earlier about running forecasts this far into the future. It does come with a lot of uncertainty. How do models handle that?
Absolutely. So there's lots of uncertainty associated with seasonal forecasting, and we deal with this using a technique called ensemble forecasting. So what we do is to run the forecast several times, and each time slightly tweaking the system, making small changes. But these changes are carefully designed to take into account uncertainties associated with the model processes as well as the initial conditions. And what you have is what's called a set of ensemble members, and one particular forecast from that collection is called an ensemble member. As with the Galton board analogy that we saw earlier, doing the experiment with multiple balls builds up a distribution of plausible landing positions. And ensemble forecasting works in a similar way, and it gives us a range of distribution of possible futures. So here's a temperature forecast for the East Pacific Ocean using an ensemble with 5 members. And each ensemble member has slightly different starting conditions, taken here as the conditions measured on 5 successive days. Now, as the model simulation runs forward in time, the spread of the ensemble increases, providing a range of possible future temperatures for the forecast period.
Phil, thank you very much. Absolutely fascinating stuff. We're going to move on now to talk a bit more about the nitty-gritty and the detail of how we generate these seasonal forecasts. And for that, well, we need another Phil. So welcome along Dr. Phillip Bett, who is also from the monthly to decadal team, a climate scientist here at the Met Office. So Phil, can you tell us first of all about how these ensemble forecasts are generated?
Yeah, so the different global producing centres all use different methods to come up with their ensembles, but they're all trying to measure the uncertainty in the forecasts in different ways. So here at the Met Office, our global seasonal forecast system uses a lagged approach. 2 forecasts are run each day using the starting conditions for that day, but with slight variations in their physical processes. The changes in the atmosphere and ocean from day to day give another source of uncertainty in the starting conditions. For the seasonal forecast for the 1st of April, for example, we would pull together the past 3 weeks of forecasts, which would give us an ensemble of 42 members in total. And we treat each forecast in that ensemble as if it's equally likely over the forecast period. Further information on the Met Office's seasonal forecast system, Glossy 5, is available on the Met Office website.
Okay, what happens next? Once we've got this ensemble forecast for the upcoming season, what then?
So next we need to calculate how the forecast compares to the average for that season. So for example, is it going to be wetter or drier than average? And to do this, the forecast must be compared to the model's long-term representation of the same season and lead time, which we refer to as the model climatology.
Model climatology, that's different to observation.
Yes, it is. So remember, because of imperfections in the model's climatology will differ slightly from the observed climatology, as shown in this example. Therefore, the model forecast must be compared with the model climatology for a fair like-for-like comparison.
I see, but how exactly do you determine model climatology?
So we run the forecast model for a period in the past, so typically 20 to 30 years. And in the Met Office Glossy 5 system, we cover the period 1993 to 2016. These historical forecasts are known as hindcasts or reforecasts. Hindcast runs are produced throughout each of these past years, allowing a hindcast ensemble to be made that can match any forecast ensemble in terms of lead time and the forecast season. And this allows the fair like-for-like comparison between hindcasts and forecasts. The hindcasts are useful for comparing with the observations of the real climate to see how well the model captures climate variability from year to year. And we speak more about model performance in our next video. So as a recap, here is a flow diagram reminding us of the process of producing seasonal forecasts using dynamical methods. First, observations are used to paint a picture of the current global climate system. This picture is then projected forward in time using dynamical equations built into a numerical model run on the supercomputer. These models produce both hindcast ensembles and forecast ensembles.
Okay, so far we've talked about creating the seasonal forecasts using dynamical models, but are there any other methods of creating seasonal forecasts?
Yeah, so before we had all these huge supercomputers as the resource to run the forecasts, people had to use simpler methods, statistical methods to produce seasonal forecasts. So statistical methods use observational records to determine relationships between the weather conditions and the pre-season climate drivers, such as global patterns in sea surface temperatures. By knowing the current sea surface temperatures and using that identified relationship, then we can forecast the future conditions. This figure compares seasonal rainfall totals over East Africa with sea surface temperatures in the Eastern Pacific over the past 20 years. The data shows that, in general, higher temperatures in the East Pacific, as occurred during El Niño events, are usually associated with higher rainfall amounts over East Africa. This statistical relationship allows us to make seasonal forecasts over this region, although other sea surface temperature drivers in the Indian Ocean can also be important to consider. One of the main advantages of using statistical methods is that, unlike dynamical methods, they're relatively quick to calculate and don't require too much computing power. The main disadvantage, though, is that they only use statistical relationships, so they don't benefit from our knowledge of the many physical processes within the climate system. They also require long records of past observations, and they assume that the relationship that we've seen in the past will continue into the future, and that might not be true in a changing climate.
Thanks very much, Phil. We've come to the end of this section now. Big thanks to both Phils. In fact, we've certainly covered a lot. We've learnt how statistical methods work by identifying relationships between local weather patterns and global climate drivers, whereas dynamical models use numerical methods to represent the complex physical processes in the Earth system. Dynamical models attempt to capture the uncertainty by generating multiple forecasts and hindcasts, known as ensemble forecasting. Hindcasts are forecasts run for a period in the past and are used to calculate the model climate. Join us again in the next video when we'll explain how seasonal forecast output is presented and how to assess forecast accuracy and skill.